All right. Thanks for coming. First, let me just say I apologize for the scheduling mishap this morning. Thanks for coming now. If you don't know, this is Engineering Elegance, The Secrets of Square Stack. If you're in the wrong room, now's the time to leave. So I'm Bob Lee. I'm the CTO of Square. And that can mean a lot of different things depending on the company. But I'm not, for example, a people manager. I'm not a marketer. I'm a technical leader, and I'm very hands-on. And this talk is going to be representative of that. I'm going to give you a quick overview of our products so you have the context for what I'm talking about. And then I'm just going to tell you three little war stories or mini case studies. How many people here have heard of Square before? How many people have gotten or tried to use it before, been able to use it before? Cool. Square started about 3.5 years ago. It was founded by Jim McKelvey and Jack Dorsey. Jack is also the inventor of Twitter, obviously. Jim is an engineer, and he founded a tech company prior to that. And he's also a glassblower, and he actually taught glassblowing at Washington University. And one day, he actually lost a sale on one of these beautiful faucets that he makes because he couldn't accept the type of credit card that the person wanted to use. So he started talking to Jack about this afterwards, and they really lamented the fact that he couldn't accept that credit card, despite the fact that they have the equivalent of supercomputers in their pockets. So that got them set on track for our first product, which is Square Register. It enables you to take payments on an iPhone, an Android phone, and iPad. And you swipe the card reader, plugs into the headset jack, and that's novel, and a lot of people focus on that. But I think like the really interesting and probably one of the biggest innovations of Square was what we did to the onboarding process. Prior to Square, if you wanted to accept credit card payments, you had to get something called a merchant account, at least in the United States. And this was a pretty arduous process and took like 6 weeks. You had to get a credit check. And what we found early on when we were building this product was that half of small merchants that applied got turned down. Obviously, we're like, this won't do. So we took a step back, as we often do, and looked at the big picture and asked how we could fix this problem. And to do it, we had to work with the banks and the credit card companies to completely reinvent this process. And the result is you can download the app, sign up, and be accepting credit card payments in 2 minutes. But not only that, we included that lower, smaller 50% of merchants and individuals who weren't able to accept credit card payments and weren't able to compete on a level playing field before. So after this, we scaled up and we started bringing more of these features that big box merchants like grocery stores and pharmacies have to small merchants. So now we have like a full register solution with items and analytics, and a lot of times these features even rival the features that you find in bigger B2B software. So we obviously attacked the merchant side of the counter, but we took a step back again and asked ourselves how we could look at the entire payment experience and how we could make it better. And starting about 2 years ago, we defined what we thought was the ideal payment experience. And that was, I wanted to be able to walk into a restaurant, sit down, eat, get up, and leave, and almost wonder whether I paid or not. And we addressed that problem with our second product, which is called Square Wallet. And the cool thing about Square Wallet is you open it up, and it shows you the list of businesses that are around you, and you can hit a pay button if you want to be able to pay at that business. And so say we're in a coffee shop, for example, and I go to the counter and I order my latte. Instead of taking my credit card out and swiping it, or instead of tapping something on a wireless reader, all I say is put it on Bob, and the technology fades into the background. You can also set up hands-free payment for businesses that you frequent, and what that means is every time I go to that business, Square will automatically enable me to pay there, and I don't even have to take my wallet or my phone out of my pocket. I think that's really cool. Like I said, whenever you're at the counter to pay, you just say, put it on whatever your name is. I say, put it on Bob. And then the merchant, on their register, they see your name and your photo. So those are our products. Let me tell you a little bit about the technology that backs those up. I'm going to tell you 3 stories. The first story is about persisting queues. First, let me tell you a little bit about how you accept credit card payments and how that works. It's actually kind of interesting. First, there's 2 steps. There's the authorization and the capture. And this is almost like a 2-phase commit. When you authorize a payment, this typically happens when you swipe the card. It does a real-time authorization over the network. It verifies that you have the funds. And it actually sets aside those funds. You effectively get a lease on those funds. So they're guaranteed to the merchant if they complete the transaction. The second step is the commit. This is the capture, or otherwise known as a capture. One of the really cool things that we do in Square Register is we do the authorization online, and we block the UI on the network. You obviously have to do that, but we don't block for the capture. And this is very interesting for a couple of reasons. One, it makes a transaction a lot faster. But two, which I think is even more interesting, is it results in a much better user experience. So for example, when you swipe the card and you authorize a payment that happens over the network, and then you sign on the screen, and then you hit continue, that's when you're basically committing the transaction. You sign, and you hit continue. At that point, instead of going over the network and posting the capture over the network, we actually just enqueue it in the background on the device, and then there's a background service that'll just keep retrying until that capture eventually succeeds. And this is safe to do because the authorization set aside the funds for, depending on the issuer, some number of weeks, but it's pretty safe to do. Well, to do that, though, we had to write, this is very serious business, right? You can't mess up these captures or else the payments don't go through, the merchants don't get paid, and Square doesn't get paid, and the buyer, walks out with the item anyway. So this code just had to be completely rock solid and robust. So how do you go about that? How do you implement a robust queue? How do you do it on the server side? I asked myself. Typically, you go about it a couple ways. One, you can just build a queue on top of a SQL database, right? A relational database. You just have a column, you maybe have a flag to keep track of which items you've processed and which you haven't. You also might use a messaging server, like message-oriented middleware. You might have a separate server. Typically would not do that on a mobile phone. So neither of these were really satisfying to me. You do have a relational database on a phone, yes, SQLite, but there were a couple of things I didn't like about it. One, it seemed like there was a lot of performance overhead for something as simple as a first in, first out queue. You're basically building on top of a B tree, and you have a rollback journal and all that kind of stuff. But two, and more importantly, I kind of felt like it had too many moving parts. This is code that has to just work and always work. It has to be industrial grade. And it's very easy to, I'd say, to misuse a relational database, and you might end up losing your data, losing the captures, and in this case, losing sales. So I decided to take a step back and figure out a better way to go about this. So how could I implement a FIFO queue? First, I thought, what properties does this queue need to have? How many people have heard of ACID before? Atomicity, consistency, isolation, and durability. These are the characteristics you need. In our case, we really need to focus on atomicity. That is, the enqueuing and dequeuing either happens or it doesn't. There's no in between. And durability. That means that if we said it happened, it happened. If the phone dies, if your battery dies, and you restart, that data has to be in the queue. We're not so concerned with consistency and isolation in this case because we're effectively talking about a single user system and there is no concurrency, so it's not really an issue. How do you go about implementing this? So as part of my investigation, I had to figure out how I can enable atomicity and durability. So I had to learn about what promises a file system makes to you. It turns out they don't make a lot. So one of the few is that renaming a file as atomic. And a lot of people and a lot of simpler implementations depend on this. Second, fsync is durable. How many people have called fsync before? Also known as sync in Java. This is basically a method or a function you can call, and whenever it returns, it's a promise that that data is on disk. And most of the time that's true unless you have hardware that lies to you. For example, if your RAID has a cache or something like that. Another thing that I found that's not an explicit promise, and certainly not all file systems provide this, but the majority and your typical file systems do, is there's a lot of consensus around the idea that a single segment or block write is atomic. What does this mean? So like a segment on a spinning disk or a block on flash, if you write that, it's depending on the size, or typically 512 bytes to 4K, that's always going to either happen or not. It's not going to get half written. And it's important to note that it's just a single segment. Writing multiple segments or blocks is explicitly not atomic. In fact, a lot of times, say you write a meg worth of data to the disk, your file system and your hardware is going to optimize that, and they might write the different parts of that megabyte of data all in a different order. So if your system restarts during that, you might find out that you only got half the data. It might be the middle half, might be the end half, whatever. So you can't depend on that. But we can depend on these three things, I think. Renaming is atomic, fsync is durable, and a single segment write or block is atomic. there's a few different approaches that people typically take when you're implementing a database. The first and the simplest is you write the data to a new file, and then you f-sync it, then you rename the file, and you have to f-sync again. So there's a couple of important things to note here. First, that the first f-sync is very important. Like if you just wrote the data and then renamed the file over the original file, then your system could restart, and you'll find out that you have an empty file. And the reason for this is, like I said, operations can be reordered by the file system or the disk, and in this case, the rename can actually happen before the data is actually written to disk. So, and then the second one, this is also important, the second f-sync, after renaming the file, you also have to f-sync the directory. And there's very few people that do this. And this is even more important with more modern file systems like ext4, because they don't write to disk as often. If you don't do that second f-sync and you just do the rename, you have atomicity. That is, the rename happened or it didn't, but you don't have durability. That means if your system restarts and that data may not be written to disk for even up to like a couple minutes, if your system restarts, then you won't have that data anymore. And in our case, with a capture, it's like we tell the user the transaction succeeded and that it'll eventually go through. But if their phone battery dies, we may not have it on disk. So we can't tolerate that. A couple other ways, this was simple, like doing the rename is simple, but like rewriting the whole file every time wouldn't work for something more sophisticated like a database. So databases take a more sophisticated approach. They typically take a couple approaches. One is a rollback log. They back up the data that's existing in your database before overwriting it, and they also, in that backup log, basically they rely on this atomic renaming, or they use like a journal or a write-ahead log. So thinking about all this now, how do we implement a very reliable queue? And our answer is actually an open source project. We open source this code. It's called Tape, and it's on github.com/square/tape. So it's very simple. It's just a Java-based queue, and on disk, in contrast to a database where it's like B trees and you have separate files for the logs and all of that. This is just a very simple file. It has a 16-byte header, followed by a circular buffer for the element data. And the elements are just stored contiguously in that buffer. The header, this is the really interesting part. It contains a file length, the number of elements, the offset of the first element, and the offset of the last element. And the interesting thing here is, rather than having to have like a rollback log and all these other sophisticated things and have like multiple I/O operations, I was actually able to make operations atomic by just writing the header. So, and the reason I can do this is because the header is much smaller than a block or segment, and you can count on that single write being atomic. The elements themselves just contain the length of the element and the data. Let's talk a little bit about how the operations work. So, whenever you're enqueuing something, the queue writes the data into an empty part of the buffer, and then it f-syncs, so we know that data is on disk. Then it writes the header. This is an atomic operation, and then it f-syncs again. So writing the header is effectively committing that addition to the queue. And note that we f-synced between writing the data and writing the header. If we didn't do that, the header could be written, but the data might not be written. If your phone dies or something like that, or your server died if you were using this on a server, in between writing the data and writing the header, nothing would happen. Basically, we just wrote the data to an empty part of the queue that we're just going to ignore. Dequeuing is even simpler. All we do is read the data and write the header. It's just one atomic write, one file operation. Like I said, contrast this with all the hoops that a database has to jump through and all the I/O operations that a database has to jump through. And then you f-sync after writing the header. Expansion gets a little more interesting. Basically, if you're adding an element and there's not enough free space in the circular buffer, what do? We have to expand the buffer. And we have to also do this in an atomic fashion. The expansion either has to succeed or not. So the way it works is you increase the length of the file. We start out by doubling and we double the length of the file until there's enough room for the element. Then you f-sync. We have to f-sync that metadata change. We're just changing the length of the file. We're not actually changing the file itself, but you do have to f-sync that still, and that can get lost. If that got lost, then and the system restarted, we'd have a truncated file. Then you copy the data, because we have to make the circular buffer contiguous again. Then you f-sync, and then write the header, and then you f-sync again. And then you add the item. very simple. So what's next for this? This is, I'm contemplating using tape on the server. Right now, I wouldn't use it on the server because you can enqueue one item and only dequeue and enqueue one item at one element at a time. On a server, if you had like concurrent usage, you definitely don't want to f-sync every time. You want to have some batching. My other idea is to elide the file system. This is kind of interesting. If you wanted like extreme server performance, we've already gotten rid, by not using a SQL database, we've already gotten rid of the overhead of using like a B tree and the rollback log and all of that. And we're just like, we're right on top of the file system. We could also, if we really wanted like maximum performance, we'd actually dedicate a disk to the queue and get rid of the file system altogether. Because the file system also has its own overhead and its own B trees or whatever data structure depending on the file system. I think that'd be really cool. And this is actually where the name tape comes from. Because the data would be stored contiguously on disk, and you'd have optimal performance, and just kind of reminds me of a tape drive. So that's the first story. My second story is about synchronizing data. We have a lot of cases at Square where we have to synchronize data across devices, and we do this through our server. I'll just give you a couple examples. We have items, item groups, your settings, your payment history. We don't want this stuff to just be isolated to one device, otherwise you'd have to enter your inventory on every device. So the way it actually works is you enter your inventory on one device, and if you you sign into a new device, all that data gets downloaded. I came up with a simple approach to doing this. On the right side we have the client. This is the mobile device. On the left side we have our servers. It uses kind of a feed-based pattern is what I call it. The first time the client logs in, they retrieve all the records from the server. So for example, they may get all the items. And the server returns all the records or all the items and a version V. The next time the client needs to sync, it doesn't have to download all the items again. It just tells the server, give me everything that's changed since version V. And anytime the server makes an update, it atomically increments this server-side version, and it can use that to keep track of everything that's changed. So in that case, it returns everything since version V, and then the latest version. Quick note about the version. Like I said, you update it atomically every time you make a change. You cannot use a timestamp for this, because obviously you could have different timestamps across different servers. The clock can change, and sometimes, even like millisecond timestamps aren't very granular. You can have like they can be like only increment every 10 milliseconds or something like that. And it's very likely that when somebody's requesting a list of items, that another update might come through and you would miss that. So it's very important to use like an atomically incrementing value. Let me give you an example of what this looks like. Say, for example, our feed uses JSON. The first time the client requests all the items, the server returns the version, which in this case could be 5, and then it returns the list of entities. And you can model this a couple ways. You can return the entire items every time if your items are small. And when somebody updates an item, you just return all the data again. Or you could model this as changes. I guess kind of like a command pattern type thing. Instead of modeling items, you can model an update to an item and then return that. The next time the client syncs, let's say we added a new item to our inventory, the client says, give me everything since version 5, and the server returns the new version and everything that changed since version 5. It's very simple. This works great on the clients. Then I ask myself, could this work just as well on the server? Let's take payment processing, for example, and we have like our payment history. We have dozens of consumers of this payment history. For example, the batch capture that happens periodically, settlement, that is, when we're putting money into the user's bank account, money that they accepted, business intelligence, risk systems, all these consumers of this data. How would you typically address this problem? Well, in a typical enterprise system, I think you use a messaging server, right? It's a very simple solution. It could be a naive solution. How many people have heard of the CAP theorem? So this is an assertion that given consistency, that is, everybody sees a consistent view of the data as opposed to eventually consistent, Availability, that is your system's always available for writes. And partition tolerance, that is whether or not your system can keep running even though you have a network partition. You can only pick 2 of those. So in this case, say for example, since we only had one messaging server, we obviously have availability issues, right? If that messaging server goes down, then our systems are down. How could we remedy that? Well, we could choose availability over consistency by, for example, replicating our messaging servers. Obviously, you lose some consistency here because the servers can get out of sync, one can go down. And the interesting thing here is, it's like we have our producing system, we have our consumer systems that we have to operationalize. Now we also have this additional tier and level of complexity and indirection in the messaging server. And messaging servers obviously have their own databases that you have to worry about and back up and keep highly available and keep running. This is great for vendors, not so great for us. We want a simpler solution. It'd be nice if the consumer could just talk directly to the producer, much like we do with the clients. We've actually done this. Instead of having a messaging server in the middle, now we can just produce a payments feed, much like the feed that we're using to synchronize data across the clients. So let's take an example. One of the examples I like to use is, say we want to compute the gross payment volume or the total of all the payments taken. In the highly available messaging-based system, the consumer or the messaging server has to keep track of every payment that they receive. Or that they've processed so that they don't count duplicates. Whereas in the feed-based approach, they don't have to keep track of any of that. They just keep track of the version and the total, which you can write atomically to a file. You don't even need a database on the consumer side for something that simple. So I kind of liken this to email versus RSS. You know how RSS is simpler than email. If the request fails or something like that, you just make the request again. It's stateless. Like I said, you don't have to keep track of the messages or have their own database. It has fewer moving parts. It has built-in batching, which is great because if we're talking over the network, you have fewer round trips. And also, I think one of the coolest parts is you have free bootstrapping. So let's go back to our gross payment volume calculator. Well, let's say I brought that up today. Well, it would start at 0, right? What would I have to do? If I had a messaging-based system, I'd have to implement some custom code that computed our current payment volume up till today, and then I'd have to synchronize that and start processing in real time. Well, with this, whenever I bring up that client, the first thing it does is requests all the records, and in this case, it's the exact same code path that it uses to sync. So you don't have to write any special code. I think that's pretty neat. Also, if you lose that data, you can just bring it right back up again. Some more ideas for this. Obviously, keeping track of, this could have some scalability issues if you have one central version because you have to update it atomically. So you could actually partition the feeds and have multiple systems all providing these feeds. And then since the client doesn't really care what the version is and it just treats it as kind of an opaque string, you could have a proxy in front of all these partitioned feeds that merge all the feeds together into one big feed, and then encodes all the versions into one version string. Also, on kind of the same note with performance, this is also very cool because you can cache and replicate the feeds. If you have maybe tons of consumers and you're running out of capacity, you can just add more. Also, how many people have heard of PubSub Hubbub? So this is kind of borrowing an idea from the RSS world. Obviously, in this case, what I talked about so far, and in the RSS world, you have to poll every time you get updates. PubSub Hubbub is a solution that lets you subscribe or tell another server that you care about that feed, and then anytime that feed changes, that server will actively ping you, and tell you to sync. So it's more push than pull, and it's also very simple. We could bring that exact same idea here. So that's the second story. Let me tell you one more. The story is about matching prefixes to strings or that sort of thing. I don't know if you know about a credit card number. It's called a PAN, personal account number. And at the beginning of that PAN, there's something called the bank identifier number. If it's a credit card, the first couple digits correspond to the brand. There's also further digits after that that correspond to the bank that issued it. So for example, if your credit card number starts with 34 or 37, you know it's American Express. There's a number of places where this matters to us. For example, in our user interface, when you start typing in a credit card number, we flip the credit card over and show you the brand as kind of an indication that you're typing the number incorrectly. And also on the server side, it's our risk systems can make decisions based on the bank identification number, for example. So we need to be able to match these prefixes to the credit card numbers that are going through our systems. How do we go about this? A naive approach would be to just do a big if-else block. This might work for credit card numbers, but even those can get kind of complicated. A couple things about this code. Don't read this code. This code is just to illustrate messiness. A couple things about this code. One, it's like error-prone, and it's buggy, and it's hard to read. And two, it's if you have a lot of prefixes to match, like you might in the case of bins, it's linear time. So the time this code takes to run is going to get longer and longer based on the number of prefixes you have. So I wanted something, this was unsatisfactory. I wanted to come up with something simpler. I started by designing, by abstracting the client away from the actual implementation. And I came up with this domain-specific language in Java that basically looks a lot like how I wanted to describe this. So you can see here it looks a lot like that table in the first slide. You just basically declare these mappings. So 4 maps to Visa, the prefix 34 maps to American Express. Now, how do we actually implement this class? The first time I implemented it, I just used a simple binary search. You could also use a binary tree, like tree map. In this case, this was actually running on a mobile device, so I tried to make it fast. In this case, I used just 2 sorted arrays, 2 parallel arrays sorted by the prefixes. And basically, all you do in this matcher is you pass it the string. In this case, it would be a card number, and then you search for that card number in the list of prefixes. Obviously, it's not going to find it because it's a full card number, it's not just a prefix. But the interesting thing about arrays.binary search is it returns the negative value -1 of where that string would be inserted into that sorted array. So you can just invert that number, invert that index, and find the next item, or the previous item, I mean, which in this case would be, since these things are sorted lexicographically, it would be the prefix. And if we find a prefix, then we return the corresponding value in the values array, which in this case would be a brand. If we don't, then we just return a sentinel that says it was not matched. So this worked great for a while until we ran into one drawback. I kind of took a shortcut when it came to ranges. So some prefixes are simple, but some have pretty wide ranges. They can have hundreds or even thousands of prefixes. And in this case, I just iterated through the prefixes and created a mapping for each item, because it's pretty much what you had to do in this case. And then somebody came along. This was fine at first because the ranges were pretty small, but then somebody came along and added a range, I think, with like a couple thousand values, which you obviously don't want to allocate a couple thousand strings on an Android device at startup. It'll make your startup slow. So what do we do about this? How many people have heard of a trie? I call it a trie. Some people call it a tree. I like to call it a trie, so you know I'm not talking about a tree. The way a trie works is it's a lot like a binary tree, except for instead of having just 2 children per node in the tree, it actually has a node per character. So you say, for example, we wanted to match a credit card number 56001. The way you go about it is you start at the root. You find the child that corresponds to the first character, in this case 5. And then you then for the next branch, you find the node that corresponds to the second character, in this case 1. And here we can stop, because as you see, that corresponds to a MasterCard. It's very cool. Whereas the first solution that we talked about was messy and it was linear time. The second solution was log in, which is very fast and effectively constant time. This one's even faster or less complex because it runs in constant time relative to the length of your card number. It's the performance, therefore, is like independent of the number of prefixes you're trying to match. And this was all great until this guy came along. This is our new card reader. The interesting thing about this is we encrypt the card numbers in the reader. So the first digits of the card number aren't exposed to the device, so the device would have no way to identify the brand. So you actually have to identify the brand in the reader. This has a little CPU in it. It's called an MSP430. Kind of the interesting thing is it has not no RAM, but very little RAM. No RAM available to doing something like this. It has 256 bytes of RAM. And in that, it has to decode the credit card number, encrypt it, and transmit it to the mobile device. So we obviously don't have much room left to do stuff like matching brands. It does have lots of flash, though, for code, like 8K or something like that. So do we go back to matching by hand? That'd be kind of sad, right? The problem with the Trie here is that all of those nodes take up a lot of memory. It's very fast from a CPU standpoint, but it can also take up a lot of memory, which obviously wouldn't work here. I came up with a clever solution to it, though. I encoded the Trie as a series of nested switch statements. So basically, I still constructed the Trie, but this time at build time, and then I wrote code that walked that Trie and then generated this code. This is actually generated code here. This is kind of a simplification of what it actually looks like. But as you can see here, so say we wanted to match a credit card number 34000. It matches the first character, 3, and then it goes to another switch that matches the second character, 4, and then as you can see, it returns American Express. So that was very cool. It uses no RAM, effectively, and basically trades code for RAM. And this is crazy fast, still constant time. Also loads a lot faster on a mobile phone or something like that, because basically on Android phones and that sort of stuff, it can just memory map in the code. It doesn't have to do much verification. It doesn't have to do any verification. It does it at installation time. So I thought this was cool, but then something I realized looking at this is that the Trie is actually a subset of an AST, you know, an abstract syntax tree, like you have in a compiler. Your compiler that compiles to Java, for example, it doesn't just read the text and then generate bytecode directly from that. It uses an intermediate representation, or kind of like an object model that represents the source code. And so this is effectively the same thing, it's just all switches. And the thing that I realized was, just like a compiler, I could actually perform optimizations on this Trie or the AST and do things like inlining and making the code smaller and that sort of stuff. I thought that was really cool, basically applying the same concepts. So this may seem like overkill for something as simple as prefix matching, but I do think it makes sense. Like I said, now you can input like an entire bin database and like match credit card numbers to banks very efficiently in a risk engine, for example. I also used it in another place. I actually have what we call a loon filter. Basically filters all our logs and watches out for credit card numbers in case somebody has a bug in their code or something and actually logs something they shouldn't. It'll filter those out. Obviously, since this is running against all our logs in real time, it has to run very quickly, so this code comes in handy. So what's the moral of these stories? It's a few things. One, like I encourage you to deeply understand your stack. It's something I definitely like to do. Like I said, whenever I implemented the persistent queue, I didn't just use a database. I really took a step back, and like I even got into like the file system code and the source code for the file systems to actually understand how they work and whether they provided like atomicity for segment and block writes, that sort of thing. I always like to always question assumptions. A lot of people just think this kind of stuff's done science, or they don't think too hard about it. Kind of like a counterexample to that, for example, is it's like take quicksort, for example. It seems like it's been done, it's been around for decades, you can't really make it any better. Not true. Josh Block was on my team at Google, and he was actually able to make it twice as fast by going from 1 pivot to 2 pivots. It was something people had considered, but not really actually tried. And so now Java sort in Java 7 is twice as fast. The other thing is, I think reuse is a little overrated. I always kind of tear up a little bit when I see developers, it's like pull like an open source jar and try to hammer it and spend 2 weeks trying to hammer it into submission. A lot of times I think it can actually make sense to build something from scratch and build it the right way. I definitely encourage people to, it's not reinventing the wheel, or it's good to reinvent the wheel if you're inventing a better wheel. If you like these stories, I have some further reading for you. At Square, we actually have an engineering blog. It's corner.squareup.com. And a lot of people post these stories, including our own Jake Wharton, who's sitting right here. We also are prolific open sourcers. If you go to github.com/square, last I checked, we had something like 96 open source repos. So there's things like tape and a lot of other open source projects out there you can check. Also, I'm at CrazyBob on Twitter. Any questions? Yep.
Just a functional question. So the time between the authorization, right, and then sending through the, I don't know how you call it.
The capture?
The capture, right? So the temporarily, the capture is stored on the device.
Yes.
Right. So what if your device breaks?
Yes, that's a great question. He asked, you do the authorization and then the capture is stored on the device. What if your device breaks? That's definitely a possibility. One thing we do is we tell the user in the notification panel that the transaction is still pending, so that they at least know that the transaction is still pending. And then second, that's definitely a possibility, but you know, it's happened so rarely, I actually haven't even heard of it happening. But they would just have to call up support, and we'd fix it for them. Yes, and they would definitely recognize that and call support.
When you expand your trie into a class, how big is this?
He asked, whenever I generate code for the trie as a switch blocks, how big is it? I think it's ended up being a couple hundred lines for all the credit card brands that we match.
You're running Java on that thing?
No, I actually generate Java and C code from the same trie. So it's nice that you can like define the mappings in Java, but it generates C code, which runs on the little reader, and then Java code, which runs on Android. And the same optimizations apply to both because I make the optimizations to the trie and then generate the code from that. Cool. Any more questions? Awesome. Thanks.